Hi, we are going to be determining the content of ascorbic acid and vitamin C today. This is going to combine labs 8 and 9. 8 is going to be the determination using an acid-base titration method. So we're going to be using 0.1 molar. This is our 0.1 molar that we're going to use that was previously standardized. Okay. Bobby and I, mainly Bobby, made up our vitamin C stock as per the instructions in the lab. So we got the mass of a whole tablet, crushed it up with a mortar and pestle, and delivered 0.5 grams into our 500 milliliter flask. You'll notice that all of this didn't go in solution because all pills that you take contain caking agents that are not going to be soluble in here. They will, however, be soluble in your stomach conditions because it's acidic, and these are mainly carbonates and such, so they'll react with your stomach acid. All right, so no worries in your system. We have already done 3 of our samples. This is our last sample. So I wanted you to see this titration. This is just an acid-based titration, so there's nothing that's unusual about it. As our pink starts staying longer, we're going to cut back our flow. Drip it in more slowly. Our pink stayed quite a bit, so that half drop that's on the end of our burette, we're just going to touch in here. That didn't do it, so we're going to take another half drop. Just as a reminder, we're using phenolphthalein as our indicator. Phenolphthalein is clear in acid, so this contains our ascorbic acid that we're actually titrating. The titrant is the base, and as this gets to a neutral pH, you need to actually look up the pH that phenolphthalein changes from clear to pink so that you can discuss that and why we're able to use this indicator in neutralization reactions. There we go. Pale pink. All right, we're going to read our burette. Nine point six two. Yeah, 9.62. All right, now let's meet at the board for our calculations for this. All right, for the math for this, what we've done is we have taken ascorbic acid, that's a double bond, sorry. Let me make that a little more clear. There we go. I have black fingers. We have our ascorbic acid. We're going to react that with base. give us, now which one of these is going to be the most acidic proton? This one's in conjugation.
So that first one you were thinking?
This is, yeah, this one wouldn't be. Yep, so this is going to be our most acidic proton. Okay, so if you need help in determining that from organic, you should remember this is going to come here. These electrons are going to come here. That's going to result in this is our sodium counter ion. Now this is going to be stabilized through resonance because you can go here, you can go here, you can go here. So that charge is spread out over several carbons or several atoms, which is going to stabilize it. That's why that's our most acidic proton. Pulling that off allows for that to occur. All right. So that will give us this species plus water. Okay. Now, we have a 1-to-1 molar ratio. So we know the molarity of our base, something, something, moles per liter. We will have our volume from the titration in liters here. That'll give us moles. It's a 1-to-1 molar ratio. So 1 mole base to 1 mole ascorbic acid. I am going to abbreviate that as ASC so I don't have to write this whole thing out or draw it out every time. That's going to give me moles of ascorbic acid. From the moles then we can go to gram amount that represents using the molar mass of ascorbic acid. So here you're going to have your molar mass of grams per mole of ascorbic acid. That will give you, that's molar mass, big M, molar mass. Sorry if that's not clear. Molar mass. That will give you the gram amount of ascorbic acid that actually occurred in your titration. Right? So we will see you for Lab 9, which is the redox titration of vitamin C. Then you'll be able to do an F-test to compare these methods to see if there's a statistical difference in the precision of these methods. So we'll see you for Lab 9.